Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fikir bin Masya and my matrix number is MH20029. I'm the one of group members for group 4. My responsibilities in this group is to answer question 1 and question 2. First of all, we decided to take uh, Tanjung Bin Energy Power Plant as our reference to done this project. Tanjung Bin Energy Power Plant, also known as T4, is supercritical coal-fired power plant located in Johor, Malaysia. This power plant is a thermal power plant. For question 1, this question requires us to find the net power output. Since the actual power output of uh, Tanjung Bin Energy Power Plant is too high, we decided to take a power of 300 megawatts only. First, I start to sketch the TS diagram to show what is the process happen in that power plant. I use the formula which is W equals to QB minus QR or W equals to Q in minus Q out, because the net work output also can be determined from the heat transfer data alone. The four components of the steam power plant involve mass flow in and out, and therefore it should be treated as open system. Q in, or we call it QB, is amount of heat supplied to steam in boiler from a high temperature source, while Q out is amount of heat rejected from steam in condenser to a low temperature sink. So, to find Q out, Zareh will explain how to find it. For Q in, we must to find the H3 and also H2, because heat input to boiler happen from process 2 to 3. To find H2, first we must to find H1, which is we can get it at table A5 at 40 kilopascal. Then we must plus it with W of pump. Then we can get uh, then we must plus it with work of pump, then we can get the H2. For H3, we can get it from table A6 at pressure of 25 megapascal. So for question 2, we need to find the type of fuel and the amount of fuel used in this power plant. So the type of fuel is coal. The power plant use coal as their fuel. After that, we must to find amount of fuel used in this power plant. So as we know that unit generated over hours is 300 times 10 the power of 3 kilowatt hours. So we need to use this formula to find the coal consumption. Heat produced, which is heat produced over efficiency. So heat produced, we must to divided 300 times 10 the power of 3 over efficiency, which is this. So we can get uh, 0.8 megawatt. Then we must to put the 0.8 megawatt into this, then we can get 0.024 kilo per second. So for 1 hours, this power plant can use 86.4 kilogram. That's all for me. Thank you.
Assalamualaikum. My name is Muhammad Ashraf bin Sharuddin. I will discuss about question 3, which is the power consumed by the pumps. So based on the calculation, pump works WP equals to V1 times by P2 minus P1. So the V1 we got it from the previous calculation, which is 0.001026 meter cube per kg. And P2 we got it from the previous slide, which is 250 bar or 25,000 kilopascal, minus by the P1, which is 40 kilopascal. So we got 25.61 kilojoule per kg. Thank you.
Assalamualaikum. My name is Muhammad Zareh Adam bin Muhammad Noor, and my student ID is MA20146. I will represent my group to explain about the rate, how to obtain the rate of heat rejection at the condenser. Okay, as we know, what we have to calculate is basically is from the second law of thermodynamics. um, and uh, and for heat, as we know, the heat flow of heat is from the high temperature to the low temperature. Okay, then and basically to obtain the heat rejection, we have to minus the amount of heat at the high temperature to the and minus the amount of heat at the low temperature, so that we can have the heat rejection. So basically the H1 minus H4 is basically the amount of heat at the high temperature before the condenser, which is from turbine, or and minus the amount of heat at the low temperature, which is H4. Maybe after condenser, maybe at the pump. Okay. Okay, then after I obtain the heat rejection, what I have to do is what I have to do to obtain the rate of the heat rejection at the condenser is the assume the mass of flow rate, which is the 0.024 kilogram per second, and then I have to multiply to the amount of the heat rejection. Then I will obtain the rate of the heat rejection per second. So the amount of the rate of heat rejection at condenser per second is for 41.3419 kilojoule per second. Okay. I also can calculate the rate of the heat of the rejection um, per minute or per hour. Just multiply by 60 times 60 or 60 times 60 times 60 point times 60. Okay. Um, okay. I think that's all from my part. Thank you.
Alright, my name is Muhammad Nakib bin Mansur. Metric number MA20169. I am responsible to present for question 5. Question 5 is asking to determine the rate of entropy generation in the power plant. First of all, we have to do the assumption. The heat transfer in the cycle is in steady. That means we have to use this formula, this steady heat transfer formula. But due to the question is asking for the rate of entropy generation, we have to use the rate formula. This is the formula. that we have to use. When s dot in minus s dot out here, this is the rate of net entropy transfer by heat and mass, while this s dot gen here is what we have to search. This is the rate of entropy generation here, equals to d system divided by dt. This is the rate of change in entropy. When steady heat transfer, rate of change in entropy is 0. That means here the system divided by dt, or rate of change in entropy, is become to 0. Alright, here this is equals to 0. Alright, from this formula, we have to convert it into this equation here. This q dot is what we have searched in the previous question. That is the heat produced, and then to find the S gen, or the rate of entropy generation, we have to substitute all our data that we have gained into this formula, into this equation, and this is the answer. The rate of entropy generation is equal to 0.171 W over K. Alright, one of the quote that we have learned from doing this thermodynamic project is, my law of thermodynamics, things get worse under pressure. Alright, that's all for our presentation for this project. Alright, thank you.